Whirling about the nucleus are particles called electrons, which are negatively charged. The electrons are relatively small in mass. Take a look at this picture for a size comparison. Now, a natural question would be, are electrons, protons, and neutrons the most fundamental particles? The answer is no. These fundamental particles are made of more fundamental particles called quarks. But we don't have to go that far yet. Just be aware that such sub-fundamental particles exist. The only fundamental particles are electrons, protons, and neutrons. Did you know what information can be derived from these subatomic particles? The number of protons in an atom's nucleus denotes the atomic number that is found in the periodic table, while the total number of protons and neutrons denotes the mass number. To summarize, atomic number Z is equal to number of protons is also equal to number of electrons in a neutral atom, while mass number is equal to number of protons plus number of neutrons. This figure shows how to write the symbol of an atom together with its atomic number and atomic mass. Please examine closely the figure. But some atoms have the same atomic number but different mass numbers. This means different number of neutrons, right? Such atoms are called isotopes. The existence of isotopes was shown by mass spectroscopy experiments, wherein elements were found to be composed of several types of atoms, each with different masses. Take a look at this sample problem of determining the number of subatomic particles of isotopes of the element silicon. To answer, we have to use the atomic number and atomic masses. So how did you find it? Try to answer activities 1 and 2 in your notebook. Did you get the correct answers? Great! Let us learn more about subatomic particles. Did you know that there are times where atoms are unstable? This is because of the large ratio between neutrons and protons. So how do unstable atoms become stable? They undergo radioactive decay. Radioactive decay is the process in which an unstable atomic nucleus spontaneously loses energy by emitting ionizing particles and radiation. This decay, or loss of energy, results in an atom of one type, called the parent nuclide, transforming to an atom of a different type, called the daughter nuclide. Atoms with unstable nuclei can undergo radioactive decay to become atoms which are more stable than their parent atoms. In the process, different types of particles are emitted. For example, a carbon-14 atom, the parent, emits radiation and transforms to a nitrogen-14 atom, the daughter. This is a random process on the atomic level, in that it is impossible to predict when a given atom will decay. But given a large number of similar atoms, the decay rate on average is predictable. So what are the different modes of radioactive decay? The first is alpha emission. It is a low penetrating emission. It is actually helium nucleus and is often represented as He mass number 4 atomic number 2. An example of radioactive decay of radium-226 is given in this equation. As you can see, the resulting atom has both mass number and atomic number changed. The atomic number decreases by 2, and the mass number decreases by 4. Because of its very large mass, more than 7,000 times the mass of the beta particle, and its charge, it has a very short range. It is not suitable for radiation therapy since its range is less than a tenth of a millimeter inside the body. Alpha particles' main radiation hazard comes when it is ingested into the body. It has great destructive power within its short range. In contact with fast-growing membranes and living cells, it is positioned for maximum damage. Next is beta particles. They are emissions with medium-level penetration. They are fast-traveling electrons. As a result of beta emission, the resulting atom will have an increase in the atomic number by 1. There is no change in the mass number. In the process, there is also a proton formation from the neutron inside the nucleus, along with the electron formation. In the following example, thorium-234 decays to protactinium-234 by emitting a beta particle. The high-energy electrons have greater range of penetration than alpha particles, but still much less than gamma rays. The radiation hazard from betas is greatest if they are ingested. Beta emission is accompanied by the emission of an electron antineutrino, which shares the momentum and energy of the decay. The emission of the electron's antiparticle, the positron, is also called beta decay. Beta decay can be seen as the decay of one of the neutrons to a proton via the weak interaction. Another mode is the positron emission, which is the positive counterpart of an electron emission. A positron has the exact mass of an electron, but has a positive charge. During this event, a proton is converted to a neutron and a positron. The product of a positron decay will have an atomic number less than that of the decayed atom by 1 unit. There's no change in mass number. Then we also have electron